What would you say if I told you that using a specific blend of resins, you could print high-performance auto racing parts on your resin 3D printer? And what would you say if I told you that those parts would be tough, high density, and pressure and heat resistant? Well, my guest in this video does just that with a resin combination we will reveal in this video. Hi, I'm Chris Lannon with Make 3D TV, and this video is the first in a series on how to make money with resin 3D printing. Today I'm talking with Tony Moura. Tony's a user experience architect with a design engineering background. He designs and sells high-performance auto racing parts as his side gig. Here's part one of my interview with Tony. This episode brought to you by Mach5.com. Check out our blackout covers, screen gaskets, vinyl skins, and other gear for your resin 3D printer. Look for special discount codes in the description. That's Mach5.com, also on Amazon. All right, well, I happen to be in the Facebook group where you were talking about doing heat-resistant components, and you mentioned that you made car parts, and then somebody asked you about what your mix was for making the heat-resistant components, and that really kind of intrigued me. So I wanted to find out more about your story.
Yeah, no problem.
So how did you get involved in 3D printing? How long have you been involved?
3D printing for probably a little less than a year, but I've got a design engineering background.
Oh, okay.
So that's kind of where I take it from, mechanical engineering, and I'm a creative as a whole. My day job is I'm what's called a user experience architect. So I design mobile and enterprise apps and interfaces, but from a human perspective, what a human actually needs. So I went to school for design engineering, mechanical engineering with focus on design. And I got started because I've got an 800 horsepower car in the garage that I was designing parts for. Everything's kind of bespoke, it's one-offs, right? And so what happened is I miscalculated a part by a millimeter. And because I'm doing it old school, just going out there with calipers, right, measuring stuff out. I sent it off to the machine shop. It came back. It was a hunk of aluminum. It was like $135. And I was so excited, went to go put it in the car, and it was off by a millimeter, it just wouldn't fit. And I was so ticked. And I was like, look, if I keep doing this 4 or 5 times over, I'm like, I've already bought a printer. I wanted one anyways to play around with. But I'm not into doing like the minifigures or the characters or stuff like that. I mean, I'll do a D&D character for like my kids or something.
Yeah.
Started out with an FDM machine and bought one for like $400. But then I didn't immediately, because I have an engineering background, I didn't want to mess with PLA right away. So I was like, forget the PLA. I want something heat resistant. It's got to go in an engine bay. Even for testing, I kind of take it to the extreme. And so I was like, I want carbon fiber and then, PETG. So I started, who's got the best PETG with carbon fiber? And then I went that route, and I just couldn't get the quality that I was wanting out of the parts, layer lines, right? The same stuff from an FDM printer. And then so I was like, well, let me go to a resin printer. And I started doing them really for myself. And then what I was doing was taking the CAD drawings of the stuff that I was making and just throwing it out to a couple of Facebook groups I'm a part of. And I was like, hey, take a look at this part that I designed. And people were like, oh, it's really cool. What's it used for? And I told them, and for me, I wanted to make sure the part worked. So I used Fusion 360, and I wanted to make sure that in Fusion 360, I would do stress analysis and test and vibration and the computational fluid dynamics testing to make sure that the part can meet the standards that I wanted it to meet to, so that when I had the completed file, I could send that off to the machine shop and I knew it worked, right? And so that's kind of where it started. The part that was ironic is I had a couple of people that were in that group that was like, hey, can you make a part for my car? Well, I've got a race car. Yeah, sure, because I'm a part of like a couple of race car groups. And I was like, yeah, sure, no problem. And even though my car is not a race car, it's on the edge of daily driver / race car. You can take it, drive it from here to the track, run it on the track, and then drive it home.
What is it? What kind of car is it?
It's called a Volkswagen R32. So it was made in 2004. It's a hatchback. So it's literally, there's nothing hasn't been done on this car. My wife told me it was 8 years is the build yesterday. It was about 45K that I've spent so far.
What year is it?
2004.
Okay. I have an S2000, a 2000 S2000.
Okay.
But it's all almost completely stock. But I remember those cars from when I used to get in trouble.
Yeah, of course, right? So
Yeah.
I probably should have left it stock, but
Yeah.
so what happened is these guys are like, hey, can you design a part for me here and design a part for me there? And I'm like, yeah, sure. And I would design the part. I don't print up anybody else's file. They were like, well, can you print something? No, because I don't know how it was designed. I can't kind of put my reputation behind it. I don't know what you're going to use it for. And what I don't need to have happen is just because I take my reputation personally, I wouldn't want you to go using it on your car and say, well, it got printed badly, right? Hey, man, it wasn't me. It was your design.
Right.
Just eliminate that back and forth. And then I went to a resin printer and I bought one Elegoo Mars resin printer. And I bought the printer, and within the first print wasn't even done yet, and I had paused it and taken a look. And I didn't even print the little test print that came with it. I threw a part on it right away. I paused it, I looked, and I was like, holy crap. Okay, give me 3 more. So I ordered 3 more. And when I started doing that, I started getting, on an FDM printer, 1 millimeter, right, is good, right? You can get somewhat smaller, but let's say 1 millimeter. 50 microns or half of that on a resin printer. I was getting parts that looked injection molded.
Right.
And I was like, yes, this is what I want. And then when I started showing those parts, then the race team started hitting me up. And the race team was like, hey, can we get these parts? Sure. What do you want? And we would sit on the phone for 45 minutes to an hour, them describing the part. This is what I needed to do. Or they would do it on the napkin and send me a picture. All right, that's kind of where it went. The printing for me is not the big aspect. It's literally the design of the part, the engineering of the part, the testing of the analysis of the part, putting it up in the cloud, letting them take a look at it, letting them take a look at the engineering that was behind it. Here's the reasons why I did this. And then from there is going, okay, do you want it printed? Yeah, okay, great. Then I'll print it. And the parts that I print now right off the resin printer are functional used parts. They're used right away. I mean, so it's kind of ironic. I mean, this is an FDM part here. This is a printed, a resin print nut. And I really wanted to see if they would mate perfectly. And they do. There's no, everybody's shrinkage and warpage and all other stuff. I've never experienced that.
Wow, I was going to ask you about that.
And these are threaded parts. So, and what happened, what I was doing is the parts that were printed on the filament printer with the carbon fiber, with the PETG, I was having to chase these threads with a big die, right? I was having to just do it manually by hand. I was cutting up my fingers because you can see the edge of this part. And I could never get it to me, people eat with their eyes. So I would want to send them a part that looked good versus, oh, it was functional, but looks like junk. And I could never get it to look good on one aspect or another orientation, because one orientation would work, it would look great. Another orientation would look like crap, right? And so I started coming up with the same parts, but making them out of resin. And the threads were perfect. I never had to chase the threads on any resin parts that I did.
Wow, I've heard people come having problems with precision, but do you think that's the resin that you're using, where you're not coming up against that? Or
resin, it's a combination of a couple different things. It's the resin that you're doing, and it's the engineering of the part. Right, so people think I can just take a part and put it on the resin printer, it's going to come out. It doesn't. There's no way it's going to come out perfectly every single time. There's another guy off of a Facebook group that reached out to me, and I worked with him for the course of probably a week and just mentored this guy from the time that he didn't know what he wanted to ordering a resin printer to getting it in. I had him up and printing within 15 minutes of getting the resin printer, and then even told him some more exotic resins to go with. I mean, he's buying resins that were like $200 a liter, right? So, I mean, super expensive stuff, super high end stuff from like Loctite. Loctite even told him it couldn't be done. I'm like, let's prove him wrong. And then so he was printing it and got it on the Elegoo Mars. I mean, a consumer printer less than $300. The resin costs as much as the printer that he was using.
Right.
And and he got it to work and he got it to print. And that was through a combination of let's mix this, let's mix that. In some cases, it's not exact formulations, It's more so like, let me eyeball it, right? I've got 90% of this resin. For this stuff, as an example, this is super high density, but this is also heat resistance to 400 degrees deflection heat. There's Frozen's TR250 is a main component of this, but there's also Siraya Tenacious D that's in here as well, in blue. And then to give it this actually even grayer color, because I was trying to get it to black, because within an engine bay, it just looks better if it's black, is I put in mica powder. And the clients actually started liking it because it gave it this satin metallic-y look to it, like it was a metal piece. And these parts have held up in an engine bay of a race car and with no issues or no problems. These little, matter of fact, these little bungs, a hole is drilled directly into an intake, and these are epoxied right to it, and then a water methanol nozzle is screwed right in here. And this is a 1/8 NPT hole. And what I'll do in Fusion 360 is I'll actually go to McMaster, because you can import McMaster parts.
Right.
So what I'll do is I'll go out and I'll use a part from McMaster that's 1/8 NPT that gives me the threads that I want. And I'll use that as like a cutting tool, like a bit in the part. So I'll import the tool, I'll have the part, I'll set it there and tell it, hey, take this part and cut it with this part, and it gives me the threads, because Fusion 360 cannot do interior, inside diameter, 1/8 NPT threads. It can't do the taper.
So you just do the subtraction.
Yeah, so it can't do the taper, but I was like, well, let me see if this works. I tried it. I'll be damned. I mean, I can take a nozzle and thread it into that 1/8 NPT hole, no problem.
So what exactly is that part? Can you describe what it does?
Yeah, so this part right here is typically in a water methanol injection system, which is used in the engine, and they use them as direct ports. And it's a combination of water and methanol. And what it does is it extracts heat, typically from a forced induction system like a supercharger or typically a turbocharger. So when you actually compress the air molecules bouncing up against each other cause heat. So the air coming out of the turbo or the supercharger typically is a lot hotter than the ambient air. Typically, two ways of cooling it off. You'll pass it through an air-to-air intercooler, which just uses the ambient outside air temperature to cool it down a little bit before it goes in the engine. Or in my car's case, it uses an air-to-water intercooler, takes the air, passes it through water, in a sense, it's been chilled with water, and it comes out the other end cooler. My car and other cars have what's called direct port, which means is each intake runner that goes in the engine for the air is you have a hole with a nozzle. And the nozzle is not very big. I mean, this is it. There's a super fine, I mean, we're talking probably not even a couple of millimeters, a couple of microns, is a really small pinhole. Under high pressure at about 120 PSI, the water from a tube that comes in the back of this comes out in an atomized mist, almost like a fog. That's taken and sucked into the piston. And I know it sounded bad to think, hey, you're taking water and methanol and sucking it into the piston. But what it does is it actually reduces the intake temperature drastically, because water is able to almost infinitely absorb heat. And what it does is it kind of flashes to steam really quick. And then when you compress it and expel it out, you actually get greater miles per gallon for what you're putting in. The other thing is you can actually take the head off the motor, and if you were to look at the pistons, they're perfectly clean. There's no carbon buildup. There's nothing in it you could eat off. But the problem that's tough is that a lot of the newer car intakes from the factory are plastic. And you have to drill a hole into it, and then you have to put a tap in it and tap the 1/8 NPT hole. It makes a lot of people nervous. Anybody can drill a hole, but tapping it, you got to buy a tap, you got to buy the die, and it just becomes a headache. And you run the risk of cracking it, because a 1/8 NPT actually is kind of like this shape with threads on the inside. And when you tap something, you're effectively not just kind of drilling the hole, but you're kind of trying to wedge it apart. And that's when you put something in here like this, those threads get tight because they kind of wedge into the funnel, right? So what happens is there's guys that have done that, gone too excited, and they crack it. And then you've got an intake with one hole in it that you can't use, that you now cracked, that might be $800 to replace as an OEM part. So the way that you fix that is you drill a hole, you take this little bung that I've designed, and it's got a little lip on the bottom of it. It sets within that hole, and it sets in the recess, so you can't miss it. And then you epoxy it around the outside edge. You put an epoxy and you bond it, chemically bond it directly to that intake runner on a flat spot. And I've got some others that I've designed that are actually made for a curve because not all these intake runners are flat. And I take that into account. And then from there, that leaves you the hole that you'll actually take this nozzle, and when you screw it in, it gives a place for this nozzle to actually sit.
Oh.
And when it sits on the inside, and then there's a fitting that's on the back side of this, like this. This fitting goes here, and then there's a tube as an example. But on the back side, this is what actually protrudes into that intake and sprays the water methanol injection.
So they don't have to tap it at all. They just epoxy that piece on the end.
That's it. They just drill a hole and a half-inch hole, and then epoxy this over the hole, and then this centers it as well.
Very cool.
There's that piece. There's another piece I've gotten kind of sent them out to all my clients, but this piece itself kind of does the same thing, holds a same type of nozzle as well. But what this is designed for is inside of a silicone coupling. So a lot of times cars, if you in other parts of the air system, there'll be a silicone hose or a coupling. And there's no way to actually insert this little nozzle into that silicone coupling. So you need this bung. You place a hole, and when you put it in there, you put the nut on the backside, and you tighten it down, and this gives you the same thing as a port, and you'll be able to put the nozzle inside of. But this one's unique because this one is, just like the other one, is directly in the airflow. But what I did is with this design as an example, and this design doesn't exist anywhere except for what we're holding in my hand, is that there's teeth on the back side of it. And these teeth actually help grab and grip into the soft silicone so it stops this from moving. The reason why that's important is that on the back side of this, see these little teeth?
Mm-hmm.
These are actually directional vanes. These are vortex generators. And if you were to spray this, what happens is the spray would just come out kind of straight like a fan. And really what you want is that spray to get intermixed with the rest of the air before it goes anywhere. And in the intake runners, that'll happen really quickly because the distance is really short. The distance is a lot longer because you're running probably a couple of feet, right? So what I did is I added these little vortex generators, which you can see are pretty small. And you put them in the direct path of the air. So as the air passes over them, and they're actually even at varying angles from each other, as they act like fins. And when fins in the water incur, they create vortices behind them. So it makes turbulent air as it passes over the smooth surface. Otherwise, you just have laminar shear. And what would happen is this item the spray would come up and just go 90 degrees because of the air going past it, which is not what you want. So by these little pieces creating those vortices of air, as the air comes across it, it suddenly hits these and it's turbulent going backwards. When it sprays and intermixes with that turbulent air. So it gives a good mix of the spray and the water methanol in the oxygen that's being transported. So it's like, that took me a couple of days to think about it. And it's like, well, what's everybody else doing? And how can I be innovative above and beyond that, right? And the race teams love that. They're like, we've never seen this. And we've got to put it in directionally. Yes, you have to put it in directionally. So it's going above and beyond what the clients expect. But to give you an example, in resin, because I only print these in resin now, all the parts are in resin. This part, from a resin standpoint, will take 4 hours to print, but that's for one, but I'll print up 9 at one time. And then I sell each one of these with the nut for $38.50. I have 63 cents worth of material in a resin in each part.
Yeah, that's amazing.
I mean, people see that on the Facebook groups, but that's not the part that's actually really exciting, right? It's like, yeah, okay, cool. The profit margin from 63 cents to 38 bucks. But what they don't see is that that's the 10% above the waterline, right? And 90% is the design that it took to get to this.
Do you have a patent on the design?
I don't have a patent on the design. It's kind of like, if somebody wanted to come up with it, I'm kind of like, yeah, I'd go for it.
Right.
I could get a provisional patent and everything else, but it's like I've done enough startups and enough companies that I'm like, I'm not going to worry about it unless it's a really world game changer, right? If somebody wanted to go off and start making these and you make a couple $1,000s, I'm not going to spend $15,000 to go get a patent.
Right. But you have the reputation. Are you the only one that makes those?
I'm the only one that does. I'm there. It's my exclusive design, and I'm the only one that makes it.
Right. So nobody else has that design. Nobody else can sell that particular part.
True. And the other thing too is I found out is I even asked the race teams, and these are like rally teams. These are guys that got millions of dollars that are in Europe and stuff like that, and some other teams. And I'm like, why do you come to me, right? Like you have all the resources in the world to throw this at it, because we don't need to hire a specialist guy and get printers and get everything else. We can call you up on the phone, talk to you for an hour. I'll sketch a design. I'll throw it in front of the camera, and I'm like, hey, is this what you're thinking about? Yeah, that's what we're thinking about. And within 24 hours or less, most of the time it's like 12 hours, I'll have a 3D CAD ready for them to go. I put it up in the cloud. They can spin it, rotate it, leave me notes. Yeah, that's great. That's what we're thinking about. From there, if they want to go to the next step, I do the analysis on it. I do the engineering. Here's the thought behind it. I've actually taken parts before and cut them in half. And then when I cut them in half on a bandsaw, I'll sand the edges. On the FDM parts I don't do it on the resin. And I'll look and see the layer adhesion. Is it sticking? Is it not? If it's not to what I would feel my standards are, I won't send it.
Right.
And the reason being is, I mean, you have a $100,000 race car. What if my part fails and destroys that car?
Right.
Or what if it destroys the car and it injures somebody, right? That's not what I want. And it's kind of ironic, I started calling it just bad monkey engineering, because I was just making a joke that I'm just a bad monkey, right? So
right.
I called it, and I don't advertise it. I don't do anything else. It's like one team talks to another or some guy talks to another. It's all word of mouth. So I might not be doing anything for a couple of months, or I might be slammed for 2 or 3 weeks straight just doing CAD designs and running stuff off on the printer.
All right. What kind of analysis do you do? You showed me a graphic. It looked like it was some fluid analysis.
Yes, so for that one is I designed for this water methanol system. I designed a lot of parts for this one guy, and then what happened is he had a T-junction, and the T-junction needed to hold 120 psi, right, maximum. And so I said, that's great, but how could I actually lower the psi in the inside? So what I did is, this is a unique design as well. You'd never see it from the outside, but 3D printing allowed me to, in a sense, put a sphere in the middle. So in the middle of the T, normally it would just look like this. In my design, there's actually a round sphere where they join. So there's smooth edges. So what happens is when the fluid comes in, it pressurizes all sides, and then it escapes where it's got places to go, but the pressure is equal. So what I did is I ran a pressure test analysis in Fusion 360, and it said it'll handle like 800, 900 PSI. So I was psyched. And I was like, okay. So then what I did is I actually did what's called a computational fluid dynamics test. And that's what you saw, which just shows these kind of particles coming in. And then how do the particles bounce off the walls? How does that fluid actually move? Actually setting that up is harder than actually running the simulation. The simulation is kind of the output. But you have to set up the water, the density, the temperature, how much pressure is coming in, the exit pressure, is it being capped off, is it solid? You set up all these variables just to run the test and to get those particles to flow the right way. So you have to take all that into account. It even has, is it oil? Is it water mixed with oil, right? So you can put all these things into it.
Now that's all in Fusion 360?
Fusion 360 does it, yes. I run on a Mac, and they don't have that capability on a Mac. They have it on a PC. I use another tool called SimScale. So SimScale allows me to do that as all these really complex. I mean, you can do thermodynamics, you can do heat, you can do all kinds of, it's still considered computational fluid dynamics, which is the algorithm that allows you to do that. But if you wanted to design a car and then say, okay, well, let me see the aerodynamics of the car, it's still a computational fluid dynamics simulation. But I'll do that, and clients love that because here, if you think about it, they've called me. I've designed a part, kind of a sketch, and just thrown it to them, and they were like, yeah, that's cool. Within 12 to 24 hours, I've got a CAD drawing. Then within 12 to 24 hours later, I've got the simulations that Fusion 360 will allow me to do, which is pressure, stress, weight, bend, all that other stuff. And then I'm like, hey, you want me to keep going? And they're like, yeah. And I'm like, okay, so what I'll do is I'll do the computational fluid dynamics simulation. And each one of these adds on cost, right? And then I do the CFD analysis, and I show that to them, and they're like, oh my God, this is awesome, we can see this. Because honestly, that's what they're used to seeing in some aspects of designing a race car. but yet I'm showing it to them on a little part that's this big. So they're getting the same technology. I mean, I was using the same computational fluid dynamics software that NASA uses for the space shuttle. And that wasn't even SimScale. I found SimScale after that. But the one from NASA, you can get for free. It's available from nasa.gov. You have to register and be approved, but it's literally the same thing for using aerospace engineering. And I use that to my advantage. I'm like, look, this is the same software. And they're like, no way. And I'm like, yeah, on this little part.
Wow.
Right?
That's amazing.
So it's going to that scale to show them is, hey, it's just not about printing something. You know, and I stand behind the work. If something for some reason fails, I have them immediately send me the part so I can take it apart and look at it. And then I'm like, there's been one part out of probably a couple hundred that was a design flaw that I fixed. But there's probably maybe out of a couple hundred parts, maybe a dozen, but it's always been user installation error that's been the problem.
Here's the formula for that special resin mix. You want to do 80% frozen TR250 resin, 10% Siraya tenacious resin, and 10% Siraya blue resin. For exposure times, you want to do 80 seconds on the base layer and 16 seconds on the rest, and then rinse with acetone.